Screen sharing has stopped, and we want to go back to recording and screen sharing. What is the screen sharing? It's here, I think. No, that is not correct. I messed it up. Everything that we covered until today's included the material on the board. The assignments that you have worked on definitely would be given to you in a slightly different form. Yeah, but all you need to memorize is that when you have an OR gate, you add the probabilities. When you have an AND gate, you multiply the probabilities. What I've shown you here on the board. All right, these are the two basic concepts that you have to remember from probability theory. And let me see if I can share the screen and describe that material to you better, but no, it's a reading part. We are engineers, so we solve problems. Okay, so it would be closer to what we have, at least. I haven't written it yet, but it would be close to what we have in the assignments. Work the assignments and try to understand them to the best of your capability here. So let's go to reactor system. Alvaro, could you check that it is recording, please? All right, so if it's recording, we can keep going. More detail about fault tree analysis. It's a very important method for designing engineering systems. So we go back to our fault tree analysis aspect here in the notes. And now, as you could see in the fault tree analysis, we are trying to catch two birds with one stone. We describe the system using, if we use probabilities and also if we use possibilities. The OR gate in probability theory is an addition of the probabilities, and the AND gate is a multiplication of the probabilities. In fuzzy logic, if we deal with possibilities, you take the maximum between the probabilities, like what I've shown you in the Costco diagram on the unit square. And for the AND gate, you take the minimum between the possibilities. So we go back to our latch mechanism here that we dealt with the last time. The latch mechanism is a mechanical description of a control rod in a nuclear reactor. Do you see that? So if that latch is pulled, then that rod falls into the reactor core through gravity, and it would be an absorber for neutrons. It shuts down the nuclear reactor. We cannot design a system like this with one single hydraulic system to pull it. So initially we started with two of them. And from there we carried out that backward chaining or deductive logic. We made an assumption that the latch does not trip. Then we said, okay, either A or B is not working, so it can fail, linkage failed, the actuator fails to retreat. So that one itself needs for both the actuator A not to work and actuator B not to work, because we put two of them so that just one of them pulling on that rod here would pull the latch and the control rod would get into the reactor. From there, we were able to calculate the probability of failure of the overall system. And in that case, we simply took again that 0.1 assumption for the failure probabilities. When you have an OR gate, the probabilities add to each other, 0.1 plus 0.1, another OR gate, 0.1 plus 0.1. Now this 2.2 and 0.2 enter into an AND gate. So the probabilities multiply each other. So that's 0.04. And then that basic event A is 0.01. An OR gate adds the two probabilities and you get 0.05 there at the top of the tree. Now, if you want to decrease that probability, what do we do? If that's too high a probability, we can experiment by adding an extra linkage here, and it will have the same value. So instead of 0.2, 0.02, it will be 0.04, and you'll find that the probability of failure is going to be decreased. So physically, we would add a third mechanism here. But you don't go in engineering design and add more component to increase the level of safety and decrease the probability of failure. What you have to take into consideration is that you add to the cost. So in that case, if you add to the cost, then you can build a car that has all kinds of features, from anti-lock brakes to airbags to maybe a camera in the back to a radar that would save you from colliding with the truck or the car ahead of you. And this is being done. But in that case, you'll find that those features are always associated with a higher cost. And that brings us back to the cost benefit ratio, in that we cannot reduce the risk to zero, but we can always reduce it and at the expense of spending money in general. As I suggested, the Boolean expression in that case allows us to manipulate the configuration. So when we took the A is equal to A or B, notice that's or B, C itself is B or C, B is C and D, an implied period here, which because it turns into a product of the probabilities, you can get a Boolean expression that looks like this. But we can manipulate that expression, the Boolean expression, by applying the laws that we studied for a Boolean algebra. And in that case, if you use the distributive law, A plus C and D is the same as C is B or C and D is D or E. I can apply the distributive law. That's the same as B and D plus or B and E, and then another plus here, C or D, C and D, and then an or C of E. And if you substitute the values for the failure probabilities in that expression, and that expression, you'll find that you'll get the same result, except then in this one, basically you have added an extra AND gate here, because you have 1, 2, 3, 4 AND gates and 1, 2, 3, 4 OR gates. The system becomes more complex, but it leads to the same values as the results. If we are dealing with possibilities, whenever you have an OR gate, you take the maximum. Wherever you have an AND gate, you take the minimum of the possibilities and substitute them right there. So I show you here that for that, this is called the minimum set expression, when you simply expand the Boolean expression to its simple algebraic components. You could see that you can add and multiply easier than if you do it like in combinations like at the top there. And this is an example here that will tell you how this is done. We took P sub A 0.01, actually like on the board. Then each one of these is 0.1 squared, 0.1 squared, 0.1 squared. So the total probability of failure at the top is 0.05. And if you consider them as possibilities, now when do we use possibilities like than probabilities? Probabilities are based on actual measurements, actual data that we have accumulated in operating a system or observing it or simply monitoring it. But we use possibilities when we are depending on a model or a guess or the opinion of an expert. It is not something that is observed. So you could see here that the probability of failure when you use the possibility theory comes out to be larger then the probability of failure. That means what? It means that if we don't have actual observation about the system, we can still design it and operate it based on our modeling. You build a computer model, for instance, but you'll find that the possibilities now of failure would be larger than if you are monitoring the system itself. After you build the system and operate it, then you can gain data, observations, measurements, so that now you base it, the design on probability theory. Now let us look at some more complex systems. So this is a system that is not mechanical. In fact, you can think about an analog of that mechanical system for the control rod latch mechanism. It's a control rod. You can think about relays that connect to each other, and you use 2 relays instead of 1. And then if you add a 3rd relay, your failure probability would be decreased in your design at the expense of some extra electronic equipment. To give you another example, we look at an electrical here example of a motor. The motor could be any motor, maybe the motor on your car. Whenever we operate motors, of course, you'll find that we have a power supply. So it's symbolized here by that battery or a voltage source. And you have to be able to turn the power supply on and off to turn your motor on and off. So we have a switch here in the circuit. This is a physical configuration. And then you worry that you may get a very high current that could burn the windings of the motor. And in that case, the motor will stop operation. So you add a fuse as a safety element. If the current from the battery or the power supply is too high, that fuse would burn and prevent the motor from burning. And the wire here is basically the resistance of the wires. If you have any wires connection, you have resistance in the wire. And now we want to design that system so as to minimize the probability of failure. So we construct a fault tree. We use the deductive logic. Deductive logic goes from, as you could see here, from the general. We make a general statement, and then we end up at the bottom here with something very specific, the failure of the primary wire or the power supply wire. But it's, as I suggested, an art and a science, and we do the deductive logic. So you set up a hypothesis. All right, the motor does not operate. So what would cause that motor not to operate? And I'll ask you today to maybe think yourself about a fault tree. Let's think, say you have a car, and the car in the winter, you try to start it, it won't start. And then think about how to build a fault tree about what is wrong with your car. In fact, we engage in such thinking when we try to repair any of our equipment. So you say, oh, the battery may be frozen, maybe the wire to the battery is, maybe the starter is not rotating because it is corroded, or it has sand from the sand that they spray on the road and so on. So I'll give you an example where you think about your own fault tree, or you can apply it to anything. Like if you have, say, somebody did it for a plane. He was a pilot and he did it for a whole plane. But the motor would not operate in thinking about what could cause a failure. If the primary motor has failed itself, it's not working, and it has a probability of occurrence, or there is no current coming from the battery to the motor. Maybe the battery, as I suggested, is frozen into winter, so you are not getting a current to the motor. And if you heat the battery, then you solve the problem. So either the motor does not operate, then if the primary motor has failed, or this is the OR gate, there is no current going to the motor from the rest of the circuit. Now, what causes no current to the motor to occur? We have 1, 2, 3, 4 kind of probabilities. The switch may be open. It's not open. It is not closed to allow the current to go through. It could be that the fuse here has failed. That's an OR. Or the primary power supply may have failed. So that's another OR. Or the wire here has failed. So some kind of, it's not conducting anymore. And that would be all inputs to no current to the motor. The switch being open can be expanded, so we go further down the tree. The switch itself may have failed, the spring on it is not working, or the switch is left open. So you can see here you have an OR gate, or it could be the fuse can fail to open if the secondary fuse failed or the primary fuse has failed. And the secondary fuse will fail if there is an overload, obviously too much of a current in the circuit, and that can be caused by a primary wire failure, so it's shorted, or a primary power failure, that's a surge in the current. And you could see here that we have in the development of fault trees, it's partly science, partly expertise, you know how that system, how that motor functions, and partly art. You learn how to generate fault trees and then program them into your engineering system in a way to minimize the failure. And if failure occurs, you mitigate its event on human life. And we worry about, of course, human life. It's very precious. As an example for this is how we operate nuclear reactors, as a matter of fact. And the same idea here, I applied it in an article. Maybe I'll let you read it, but I didn't publish it because I don't want to get into a morass of people who lost their lives in those accidents with the 737, suing Boeing, and then Boeing suing me. But this is a nuclear reactor control system, basically. And definitely we need to construct a fault tree that describes how the failure can happen in a nuclear reactor and how to prevent the failure from occurring. So this is a diagram of a nuclear reactor. You'd have the pressure vessel here. This would be the core of the reactor where you have the fuel, and you have control rods coming from the top. And immediately you could see here the electrical analog of our latch mechanism. So you'd have the control rods here hanging, and you have 1, 2, 3 coils, magnetic coils. You generate a current that goes through them. You create a magnetic field, and that magnetic field keeps the control rod suspended, the same as the latch mechanism. And then if you remove the current from that coil, definitely now the magnetic field is not going to keep the control rod out of the system. It is dropped into the core and shuts down the chain reaction. We don't depend on a certain, only on one group of control rods. You could see here that we have 2 groups of control magnets controlled by 2 different systems. And in that case, the operator monitors some very important parameters on his console. In that case, he's considering the low pressure in the system. If you get a low pressure in the system and you have sensors to measure the pressure in the pressure vessel, this means that the coolant here, which is under pressure, has leaked. And that would have leaked, for instance, by an earthquake breaking those pipes. So a sensor that measures the pressure. And you also measure the water level inside the core. If the water level in the core goes down, so this is low level here, then of course the core is uncovered. And if you don't provide cooling, you would melt the core. Chernobyl, Three Mile Island, as well as Fukushima, all face that same situation. And you also measure a difference in the temperature of the coolant. If the temperature of the coolant coming out of the core is high, you have a thermostat in that case that measure the temperature, the delta T in the temperature. Now, you don't use a single instrument in the measurement. You use more than one instrument. And why? Because one instrument can fail. So you get basically a differential kind of a logic. You would have 3 sensors measuring the low pressure in the system, and you don't believe what you get just from one sensor. 2 out of 3 logic, it's called, sensors must tell you that the system has a low pressure, because one of them could fail. And the low water level also, well, water level is just the water level, but you have also 2 out of 3 logic for the temperature. So you have 3 thermostats that measure the temperature, and if 2 of them tell you that the temperature is too high, you believe it. Otherwise, you don't believe it because of the possible failure. You don't depend only on these 3 inputs here, and you could see that this is a logic train and a sum that will be an OR gate. Either this or this or this would happen. If that happens, you insert, you have a circuit that now goes and insert the bank of control rods. We are showing only one here, but it's a whole system of control rods. And you don't only depend on one of them, like in the latch mechanism. You have basically 2 interconnected systems. So you have a logic train that we call the A sum and another logic train, the B sum. And this is a suggestion to the Boeing company. Again, they cannot depend on a single sensor to tell them what is the angle of attack. They must have maybe 3 of them. And if 2 out of 3 tell them that the plane is not having the right angle of attack, that it's going to stall and fall like a rocket to the ground, then of course you can save lots of lives. So they can learn from the nuclear industry here and the electronics that were developed in that case. So you could see here for the pressure, we have 3 channels of reactor pressure transducers and instrumentation. For the pressure itself, we have 3 channels of reactor. This is the water level, low level for water level instrumentation. And we have 3 channels of temperature transducers and instrumentation. And all these sensors are shown there for the operator at his control, basically on the control room in front of it, the control screen in front of him. So first thing then in the control of nuclear reactors is that we have to understand the interconnection between the temperature measurements, the water level measurements, and the pressure measurements, and not depend only on one circuit to control the system. We have an interdependence between 2 of them. And that shows in, obviously, the fault tree. And now it becomes a complex fault tree, as you could see here, but we try to attempt to understand it. You have basically, you make the, if you want to construct a fault tree and calculate the probability of failure, you have, you start with the top event, the failure to trip for a small LOCA. LOCA stands for loss of coolant accident. Actually, this is what happened in the 3 Mile Island situation. You have here 4 input to an OR gate, and then the failure to remove the power from the trip bus for a small break LOCA. You could see that now 2 systems have to fail. Like in the latch mechanism, you have 2 hydraulic cylinders. This is the left side of the control system here, which we call the trip logic A sum, and the other one is the trip logic B sum. And both this and this should fail for us to fail in inserting the control rods to the reactor. Now, these fault trees can become quite large. They can cover a whole table in the operation rooms of a nuclear power plant, but then you find that, say, train A logic faults or train B logic faults, you find that it gets an input here. When you see that triangle, this is an input from another part of the diagram, and this is an input from another part of the diagram. You develop the system using deductive logic. Deductive. You go from something general to something specific, and it helps you identify the faults, and it helps you improve on the design if you need to do it. Now, this logic here is deductive logic, and the method is, as we called it, fault tree analysis. But there is another method that goes the opposite way in logic. The opposite of deductive logic is what we are going to call inductive logic. So we collect the data here from the bottom, and instead of thinking what caused the top event here, the general failure, we start from the bottom and go up to the top. And this becomes in logic. You are learning the algebra of logic here, inductive logic. And you did it in mathematics when you had, say, sequence 2, 4, 6, 8, 10. And you said, oh, I use mathematical induction to say that's a sequence n plus 2. You are increasing the numbers 2 at a time. And that's what we'll do after the test on Friday. And just have a nice afternoon. Work on the assignments if you haven't, and get ready with something similar to what we got in the assignments. All right, thank you very much for your attention. We need to stop the recording. Did you log me out? No, it's still recording. Here we have to stop it.